Salt.
Yeah, yeah, it is.
Yeah, they like drop, they like jumping down and then people are
Dude,
Yeah.
you gotta get
They're getting like Starcraft was like
Yeah.
lowest, not lowest, but like lowest money making game.
Start now. So
Alright.
first we'll start with where we left in the last test session. We made a small mistake. We'll rectify that and we'll get on with today's problem. So basically, we were talking about given a base network, which may look like see, then how do we calculate something like probability of B given C, right? So we are saying something like this, and what we did was we want to introduce the parents of A so that given the parents of A, this will become independent of others and things like that. Right? So for that, what we did is basically this is what we said. So assume that A is true, then with this probability A will be true, and then what is probability of B? And then with this probability not A will be true, and so on. So what we missed is that A being true or not is actually influenced by C. Those two are connected, right? So this is wrong. So the way to do it is actually we should always start introducing in the numerator, not in the evidence. We cannot introduce something directly in the evidence. So what this happens is that AB given C plus B not AB given C. So this way, we are not changing evidence, which is C. So this, when you do expand it, then this is basically E, A, B, C, given C.
Oh.
So this you can write in terms of variables, right? So this is basically B given A comma C to B AC, which is P. Okay, right. Okay. So in this you can further write it as so B given A comma C is basically A, and then this is BC given A multiplied by
this is all to do probability of B given C.
Yes, probability of D given C.
And that first line is wrong.
Yeah, this is wrong. So we can't introduce something directly in the evidence. Evidence is whatever it is, and then you can consider, plugging in variables here and all the combinations. So when C is true, B may be true or A may be true or not true. So we'll just sum up all those cases. And we care about where B is true. Others can be true or not. Okay. So, and these are directly available, right, from the CPTs of this network. Given A, given not A, those are available. C also, given A, given not A, those will be available. And we'll also know how to compute C, right? So all the terms in the numerator are directly available from CPTs, and PC can be calculated, in conjunction with basically PC is PCA. This is basically P, C given A, PK. And these are all available from the CPTs. So basically, we have PA and P naught A from CPTs. Basically, this is just 1 minus PA. And here we'll have PB given A and PP given not A. Similarly, PC given A and given not A. All these values will be part of the sequence. And basically, in order to find this, we have to get an expression in terms of these known values, which we did. Yeah, you can ask me questions on any of the topics for tomorrow's test, and we can do it on the board.
Can we revisit the Homer question where he goes over the weakness? Have you studied the homework? Can we just go over the, I understand soundness, but I'm still having trouble wrapping my head around. Okay, so this is my question.
See, that was the problem.
Yeah,
It's like two children.
okay, so there's the following, if we know
So they
A
have
or
a
B, we
relation
know
to each other,
not A,
C,
we know
right?
right?
But
Does
you're
it
also
show that
the
it
relation.
sound using the truth
You get to
table?
something
Then it
where it's
asks
just
us to
B
use
from A, C from A, A, C.
And I was able to do this
Yeah.
part, but I'm still a bit
Okay, then we
confused
need to fill in all
this.
those.
What is this
So it's not bad to do that. It's actually not that many manipulations, but it's kind of tricky because the notation's like unusual.
You messed it up.
Yeah. Well, I mean, it's hard to remember like.
Sounds.
So I'm just going to erase this.
Oh yeah. B given C is always equal to B. We always add in A and not A. And then like the same if we have it given, we just have it as a true divided by the probability of it. Like those rules. There's a lot of manipulation.
So the question is, the knowledge base is basically and we know not A. Can we derive?
What is this from? I'm sorry.
The homework we just did.
Oh,
This
okay.
is from homework.
Gotcha.
And they're saying show that this inference is sound, this is given, this will lead to this. Using truth table method. And is it complete? And can you show that this is a special case of resolution? So I think basically completeness here refers to
Show you the solution.
is this all what we can derive? What else can you derive from this?
I don't think so.
Is that what complete means?
Yeah, I think so.
So,
Because
like,
otherwise, basically to show that given these two, whether this is true or not.
that's the only thing that you can prove to be true. That's what complete means.
Yeah, completeness meaning basically.
Okay.
Is it the only other information which you can get from this?
Yeah. The solution's right here. It says, it is not complete by itself. And case analysis can show that this, what does that mean?
Not
I don't know what the solution
Derives
be. What's the solution already? I thought he didn't post
He
it.
didn't post it. He didn't post the solutions, did he?
Huh?
He didn't post the solutions, did he?
Yeah, for the homework you did.
Oh, he did?
The one that was due 2 days ago?
Yeah. Oh, where is it?
Are they on Piazza? Or is it on
Oh,
Blackboard?
okay, it's on Blackboard.
Oh, okay.
I look on Blackboard.
So you were right about the whole deal.
Oh, yeah. For what, for sound system?
It's like twice as much to get half as many almonds. It'd be good for a good images.
Yeah. Yeah.
Oh, you are?
Oh, a hamburger is only $1. But
It
broccoli
sounds
is
seven.
like $5.
So
Yeah.
completeness is generally referring to have you explored all cases?
What do you mean by all cases?
So maybe an example where there's more than one case, I guess. Is there an example we can think of where?
What does cases apply to?
So basically, if A or B is given and not A is given,
Yeah.
what all can you know about the space? So that's where we do resolution rule and other resolution rule, get all new clauses and things.
So if that's not complete, what is something that is?
Yeah, so here they meant something else actually. Here they're assuming that these two are given and they are asking the question whether B can be or not.
I mean, I understand how the sound is, too. The sound is, you just have to prove that wherever the knowledge base is true, your goal is also true.
I said what complete is if A or B is true.
Oh, did you see that?
Then there are certain cases
So I
where
have to
Yeah,
click
fine.
on, click on there and it's
so
like,
if not A is false, it means A is true. It means A or B will always be true.
Because you haven't come and visited him. So you're on there.
it's like when the dawn, I said that in the video, and I was like, on this day my dog's with.
Oh, yeah.
Okay, so where is this supposed to be?
A or B is true, that's and not A is true.
I don't know. I was just in his office hours, like,
Almost complete solution.
The way they are looking at it is basically
just can't bring
A or B
Can't.
and not A.
I don't know. I feel like I've asked him one. I've also asked him one.
They are saying we
Can't
can
wrap my head
derive.
around. That's how it's a special case resolution, right?
Yeah.
You
It
just,
does make a special case of
you
resolution.
just apply resolution to the knowledge base.
Is
And
this-
negation of the antecedent.
This inference complete.
There's this little slide that says,
Not a real.
It says if you derive, it's one, salvage is, if you can entail something, you can derive it, like, derive it, you can entail it.
Hmm.
But, or it might be the
This reminds me,
opposite.
like, sort of. So, I did. Yeah, actually, I might have gotten the first couple,
So it means you just, since you can't derive
but I
it
didn't
here,
do
then
this.
it's
And I
just not
definitely
moving,
didn't do
that's
this.
what it means.
I think that's what I think.
That. Nope, didn't do that.
Because the way I thought about it was if you have not A equals false, it means A is true. A or B will always be true regardless of what B is.
Probably got that one wrong.
A is
Okay.
Wait, say that.
So we did
So the
the
cl-
good one.
not A is false.
False, that means that means.
Oh, shit, didn't this.
So,
Which
yeah,
is-
I think
Oh, I didn't do
basically,
that either.
If you can't determine
Probably
what
if-
B is based on.
if this were to be used for, say, theorem proving or something, instead of using the inference rule we know, can we just use this from now on? Maybe that's what they mean by completeness, right? Then you need something like if A or not B is given and not A is given, then what happens? Then we can say not B. Not B.
I was thinking about the jokes I was just making.
Say that
I'm sorry.
just by using this.
Good thing no one said you
I
figure
don't
out
know
how to
what
do it.
they meant by completeness. I can ask and, get back. Maybe by
You can tell someone points it out. Who was it that said?
Inference rule being complete is something we don't know. We talk about methods being complete and rules being sound and methods being sound. The rule itself being complete is, I don't know. You say whether the rule is correct or not, it is sound or not, or valid or not.
At least everybody here.
When you speak of methods, you talk about completeness.
Did you guys get number 1 for that homework? That's the long one. The one that had a bunch of
I
words.
didn't label all the mutex.
Oh, yeah.
Only like 3 or 4 mutexes here, like 100.
Yeah, he.
Not literally, like get a one.
I did not.
The last part of it, but I didn't even see all of them. I talked to him about it an hour ago.
Anything else? Any other?
What's it?
We have policy attrition. What's policy attrition, possibility to value attrition, policy attrition.
All right, what don't we
You
know?
didn't attend that presentation? Okay, yeah. So the question was basically what is the difference between policy iteration and value iteration? We have covered it in previous presentation, but we'll talk about it again. So the way basically value iteration works is that first you try to get the expected utilities for all the states, and then how do you decide moves based on sigma of the transition probabilities into the value of whichever state it leads to, right? So for each A you compute this, and whichever A gives you promises maximum value, you choose that action. That's how we do in value iteration. First determine V, find V, then you can get actions by going over all the sums for all actions, and whichever action gives the maximum sum you can take that. That's how you get policies using value iteration. In policy iteration, what you do is you start with any random policy. So you assume that given some states like this, let's say, and you can move like this and so on. Right? You start with any policy. In A, I choose this policy. In B, I choose this policy. Okay? Sorry. In A, I choose this action. B, I choose this an outgoing action. Maybe this. C, I choose this action, and D, I choose this action. Something like that. So this becomes a policy, random policy. Whenever I'm in A, I will take this one. In B, I will take this one. C, I will take left, and D, I will take down. So you take that random policy and you get the values as per that policy. So the way to compute values as per that policy is once again V of S is given by reward for that state plus sigma of S of, the policy, so whatever is pi S and then V of S prime. Okay. So you'll get some value function for each state according to the policy pi. Initially it is random. Then you try to iterate over that policy. Now since you have the values, you can basically once again do this, similar to value iteration. See if any action is different from the action you already have in your random policy. If some action gives you a better value than what the current action gives you from your policy, then you change that action, right? If some action A is better than pi S, then you make pi S equal to A. So you will get a new policy pi dash for the second round. Okay? And the same thing once again. Once you have a new pi dash, you once again obtain value for that policy, by solving this equation for pi dash instead of pi. And then you once again update pi dash to new pi double dash or stuff like that.
When we start with the random policy, how will you get the V of S dash? V of S dash is the...
Yeah, so this is basically, this is solved iteratively. This is the Bellman equation. So you can assume something like Vk of S is equal to Rs plus and then Vk minus 1 S dash.
So initial values would be 0 here.
Yeah, we assume that initially 0
When we start,
and you keep iterating till Vk equals Vk minus 1.
so that
Which effectively means this got satisfied. So that's how you determine V which satisfies this.
when we start with the random policy, initially we take the values of the reward as the value function.
Yeah, when we start with the random policy, we have to solve this equation to get the values.
In the first step, that means that the reward is just the value.
Reward. So initially you could make V0 to be 0 for all states.
And the reward is constant, right?
For all S, if you make it 0, then you can get V1, V2 and so on until Vk is same as Vk minus 1.
Is the reward constant?
Rewards are not. Those are also given. That's part of the problem.
And then for value iteration, so it looks like the value of a certain action depends upon the neighboring states, right? So what would prevent the way we are considering this to go into an infinite loop where the next state is dependent upon the previous state, and then right? Because just as I can advance to a state X from Y, I can come back to state Y from X.
Yeah. So the property of this is that we also had this. Yeah, this is important. We missed this. Right? We also had a discount factor, right? So that makes sure that it actually converges, and that is less than 1. Or if you are looking for only finite horizon, it definitely converges because you will only look at k steps. And if you are looking at infinite horizon, you will have some discount factor which will make sure that it won't diverge.
Given that policy iteration takes less number of iterations to solve the MPP question, how come they both are doing almost same number of operations?
Which one? Policy iteration will take less number of iterations that are
compared to value iteration.
no, it has two levels of iterations, right? Firstly, you will iterate over the policy. You have to determine value for that policy, which will have its own number of iterations there. So you will have two levels of iterations: iterations for determining the value and iterations for changing the policy, updating the policy.
But it does converge faster.
Yeah, I mean, so the advantage here is that whether it converges faster or not depends on how good is your initial guess. So if your initial guess seems to be very close to the solution, then it will really converge very fast. If it's extremely bad, then both will become equivalent. So these are neatly worked out in that MDP recitation video if you want further details.
So MDPs give policies, right?
Yeah, policies.
Okay.
For each state, what is the action?
Do you briefly go over how you mark retexts and planning graphs?
Sorry?
Retexts and planning graphs?
Yeah. So mutexes in planning graphs is about basically making sure that all the terms in a particular level are consistent with each other. Right? So, okay. So you will have an initial set of literals which are true, and then you will apply all actions, and you will have these plus the new ones, right? And that's how you proceed further. You apply all possible actions whose preconditions are satisfied, and you will have all the ones carried plus whatever are the new ones. Right? And we know that this can't be the case sometimes, right? Suppose here there is some A true and here there is some not A true due to some action, then it can't be the case that both will coexist nicely in this. So what we do is that we put a link between the two, saying that these two cannot be true together.
And you also have retext actions.
Can we also have
But there's
actions? No, really. So basically, when do we put these arcs are decided by two rules. One based on whether the preconditions themselves are in mutex, or whether the effects of these two actions from these two are leading to something which are not consistent with each other. So that's how we determine whether two literals are in mutex or not. And what we want is that given a goal specification, we want to see that what is the first level in which all those literals coexist without any arcs between them. Then we'll know that they have actually reached there in some consistent manner.
So you mark all variables in the text that are either A, not A, or the
Yeah.
variables that stem from a condition that
Yeah, now
is
if
not A.
some other action is dependent on not A and it gives B, and some other is dependent on this gives C, then B and C will also become mutex, because these two were inconsistent.
So is that again B and C,
Yeah, so
the
if B
statement?
is the result from not A being precondition and C is the result from A being precondition, because these two are in mutex, B and C will also be in mutex. So those two can't coexist. So if your goal has B comma C in it, then this is not the level where you have reached your goal. Maybe later.
Do the mutexes decrease monotonically, because in the book it says that mutexes decrease monotonically?
Mutexes.
So I was under the impression that it decreases monotonically, and in the homework I didn't mark the mutexes in the second level, but in the solution I saw mutexes are still marked in the second level.
Yeah, it will decrease monotonically because a lot of actions won't be applicable. Right? So you will only apply So,
But they don't necessarily decrease in the levels that we are working on, right? Or is it that it has to decrease? The homework solution says the mutexes don't decrease. It implies it doesn't decrease, but yeah, in the book it says it decreases.
so where is the homework question? Maybe for that question it's decreasing.
No, in the homework question it was not decreasing as per the solution, but in the book it says it decreases.
Oh. Both are contradictory, right?
Yeah.
Yeah, so I don't know about the homework question, but basically the thing is whether mutexes decrease or not, the process will converge at some point.
They do.
Yeah. So that's all we care about. The important thing for the algorithm is that after some time both consecutive levels become same. At which point you stop.
And mutexes will reduce.
Mutexes, whether they will reduce or not, I think is problem dependent. So that is not necessary for the termination of the algorithm.
Okay.
So, but I mean, by the way, based on what you are saying, it seems to be in a contradiction.
Yeah.
For that example, they seem to have shown that mutex are increasing, where the book seems to be saying that.
No, I think my understanding is contradictory, so probably I don't know. Maybe I'm wrong. Let me see.
So does level convergence also depend on if mutexes change, if they're added or taken away?
Mutexes, no.
So
Convergence won't depend on mutex.
variables.
Convergence just depends on the number of literals there. Mutexes actually increase, right? Initially, you won't have any mutex, for example. Next level, it will actually increase.
Yeah.
So,
I have a question in progression.
yeah.
While doing progression, the first step, if three actions are applicable, like we bring three more states, and for each state we'll draw a relaxed plan and you calculate the heuristics, right?
Yeah.
So that means like for progression, we have to calculate a relaxed plan for all the states.
For all the states, yeah.
But in regression, like we need to expand only one, we need to calculate only one relaxed plan.
One relaxer from the start to the end. And you can do analysis on that too.
Like when we start from the final stage, like we might get some good states in the last part of stage. And how will we give the values of heuristics for those states based on this equivalent plan? And that is some confusion.
Okay. So, in regression, if we have